Okay, so hello again. This is the part 4 of our exercise, our bonus and optional exercise. And now we will be talking about wellhead protection areas. Alright, so I already discussed wellhead protection areas in lecture 1. Alright, so I'm gonna jump on to the problem. So let's look for that example. Example Example 16.2. So a WHPA or a wellhead protection area is to be delineated around a municipal water supply that pumps 350 liters per second from an aquifer with a saturated thickness of 25 meters and a porosity or an effective porosity of point 0.2. Now your problem is viruses. Alright, so we are concerned about viruses from residential septic tanks. Alright, so so remember that viruses can originate from sewage. If you might be familiar with the SARS, with the Hong Kong SARS, I think almost 10 years ago, the Hong Kong SARS initially spread out from the fecal remnants first of their patient zero. All right, so meaning the first one of the first infected of SARS of the Hong Kong SARS pooped on a toilet, and his poop had Hong Kong SARS virus, and then his poop somehow traveled throughout the sewage system of the hospital, and from there it spread out, all right, through the city and eventually to through Asia. All right, so going back now, the potential source of your viruses in this problem is your residential development. Okay, so there's gonna be so you have houses, you have people, they have toilets, they poop, and their poop might have viruses. Okay, okay, and then so at this moment, this information is irrelevant. So yeah, and then each septic tank of the houses in the residential development is expected to have an output of 50 viruses per liter. Alright, upon doing some risk analysis, they realized that the allowable viral concentration in water is zero point 0.2 counts per liter. And then they used and then their estimated biological decay constant is zero point 0.5 per day as per Yates 1987. All right, so this 1 square kilometer is not so much relevant in this problem. Okay, so let's explain this step by step. So basically, we just have to find the time T that would allow your 50 count per liter concentration to reduce into 0.01 count per liter. Okay, so all you have to do is use this equation, this first order attenuation equation. So C is your is your final concentration. Wait a minute, sorry. let me double check something. I mixed up something. Point zero 0.01 C naught is 50. So this is wrong. So C. Okay, so I have the same answer but wrong solution. Anyway, so I corrected that. So C is our final concentration. C naught is our initial concentration, and then lambda is our decay constant, which is zero point 0.5 per day as per the Yates 1987 study. Right, so you just have to plug in the values in this equation, and you just have to take the logarithm ln, or the natural logarithm of divided by C naught, and then that quantity is to be divided by negative zero point 0.5, and you get 17 days. So all you have to do in order for the virus to reach safe levels is to stay away from it for 17 days. Or make sure that before it reaches the well, it has traveled for 17 days, 17.3 days before it reaches your wellhead. Right? So now our problem is, what is that distance that would allow the contaminant to travel for 17 days? Okay, so note that when you have a pumping well, your contaminants are actually traveling slightly faster because your well is pumping in water, so it sucks in your contaminants. So we use here the well continuity equation, wherein r, or radius, is equal to square root of your pumping rate times time divided by pi, and then b, or the thickness of your aquifer, and then n, or your effective porosity. All right. So let's look at here. Let's check this. The inputs here. As per the example, the pumping rate is 350 liters per second, and then the time of travel is 17.3 days. Thickness of aquifer is given. It is 25 meters, and then the effective porosity is zero point 0.2. So once you plug that in, okay, you just need to plug that in. You just have to convert some values here, and then you plug in all those values in the equation. You get 181.9 meters. Alright, so that should be the distance that your contaminant will travel before it reaches your wellhead. So that's quite a large wellhead protection area. You have a 200 meters distance. All right. That concludes problem number 4. All right. So the next video we will be talking about the economic feasibility study.